Let's get started. Thanks everyone for coming to this control seminar. Today we have Professor Wang from Department of Mechanical and Aerospace Engineering at the University of Florida. And he's a group lead in the autonomous and connected vehicles at UF Transportation Institute. He was a postdoc at the Department of Electrical and Computer Engineering at the Duke University. And he got his PhD in mechanical engineering and a master's degree in statistics and mathematics from the University of Illinois at Urbana-Champaign. His research focuses on autonomy, cyber-physical systems, formal methods, and machine learning. And today he's going to talk about learning-based planning for linear temporal logic objectives for autonomy. Okay, so let's welcome Professor Wang.
So thanks a lot for the introduction. So I actually changed the presentation title a little bit. Previously, it was a theoretical foundation for learning-based planning for LTL objectives. I guess that scared a lot of you off. So I changed this title a little bit for autonomy to make it less technical. So this is our research group. We call our lab is called Smart Autonomy Lab. This is a photo from our group taken last November. As you can see, we're in Florida, so everybody's wearing shorts and t-shirts. And on the right-hand side is a set of toys, that expensive toys we have in our lab. We work on autonomy, generally autonomous systems. These include, lab-size autonomous vehicle, robotic arms. We also have a traffic sandbox in our lab for the vehicle to run. And also at the University of Florida, at the UF Transportation Institute, we are also building a car with autonomous driving capability. Basically, we took a Toyota Highlander and tried to do reverse engineering and by-wire modifications and add a bunch of sensors so that it can drive by itself. That is basically what we call autonomy. Autonomy is basically we are trying to design systems that can perform complex tasks by themselves. When you look at autonomy, although all these autonomous systems, they look very differently. Generally, if you want to realize the full autonomy stack, you basically need to do three things, and that is sensing, planning, and control. So sensing is basically you add a bunch of sensors to your system and try to figure out what the current location of your system and what is the surrounding environment. And then you send it for planning. Basically, for example, I want to do a navigation task. I need to generate a set of waypoints. When I'm doing the planning, basically, I chop the whole state space into different partitions and think of them as discrete states and generate a bunch of waypoints. And then I can design a control algorithms to track all the waypoints to lead me from my starting point to the final destination. And then I apply the control. Action, and the position of the system will change, and I'll do the sensing again. And by basically of all the autonomous systems, implicitly on the algorithmic level or on the framework level, we're basically repeatedly following this closed loop. I would like to clarify that actually in many cases, the planning and control, the division of planning and control is not a dichotomy in the sense that, the reason why I want to separate them is because, in the end, all the dynamical systems are continuous, right? Like they follow Newton's rule. Therefore, if you want to really look at an autonomous system, their governing equation is given by differential equations. But in many cases, directly handling those differential equations are very hard. Therefore, you want to do some abstraction of your basically simplification, reducing the model a little bit into the discrete domain, right? Basically, you're chopping up the continuous space into a finite set of states, and then in that sense, you basically remove a lot of complexity from the dynamic perspective and turn it into an easier planning problems to work with. Such a stack of planning and control are usually work well if your planning problem is too hard, right? Because when you are if you plan a path, when you actually use the control to follow that path, there's always an error margin. If that error margin is tolerable, everything is fine. But if your case really requires, very aggressive maneuvering, like, you are flying a drone, for example, cross a loop or whatever, then in that case, this kind of dichotomy does not really work very well. But in our research in this talk, we are basically following this paradigm of discretization. Basically, we are still doing the planning of the discrete states. I think there are very latest planning methods that directly handle continuous dynamics, either based on model predictive control, whatever. But we will not move to that domain yet, and we'll look at these discrete control problems. And in many cases, even if you are devising, complex geometric planning algorithms, in the end, you have to boil everything down into a computer algorithm. You are finally, and if you want to run it on computer, you are finally doing some discretization in some way. But here, we just do a brute force discretization from the state space level. Okay? But there might be smarter ways to do that, but this is the formulation that we are following here. So moving on, as you know, after we discretize this state space, then we end up with a finite state model. And as most of you know, the most common planning model is based on Markov decision processes. So here is an example showing what is the Markov decision process. Basically, you have a finite set of states and finite set of actions determining how you would like to jump between different discrete states. And there is a transition probability to tell you that if I, at one state, take an action, what is the probability distribution of the next state? Okay, so why do we want the probability transition here? There are many possible sources of transitions, right? There might be, natural randomness in your sensing actuation or in your dynamics that causing the randomness, or the randomness may be used during the model discretization method, right? There are techniques where you can discretize a continuous model into a finite state model while using some probability to cover the uncertainty. There are model reduction methods like that. So the randomness may also come from the discretization. You may start with a discrete continuous model. After you do the reduction, you still have some randomness here. So, and that is the most common planning model, and we are using this planning model. There's a little bit difference from the common MDP. The model that I'm going to use today is called the labeled MDP. This is basically adding another semantic layer about the MDPs. Okay, in a traditional MDP, all the states are the same. And here we're adding some labels. We associate labels, basically Boolean variables, upon the states, like to indicate that whether this state indicates a wall or this case indicates a window or whatever. So basically by doing so, by adding those labels, we create an extra semantic layers on the Markov decision process. And let's see how the planning works in that context.
Can I understand that the specific meaning of the label is that to show this state is safe?
Yeah, you can say safe and non-safe is also a kind of label. Basically, you can define whatever label you want depending on the context, but that label has to be discrete, has to be a Boolean. You can think of it as a Boolean variable on the functions, and it is true on certain states, on the labeled states, and it is false on the unlabeled states. Any other questions? Okay, so on the MDPs, we know there a lot of problems has already been solved pretty well, right? Now the MDP, the navigation problem from one point to another is actually well solved using dynamic programming. But usually when we talk autonomy, right, we are not, if a car can go automatically from point A to point B, we generally still don't want to call it autonomy, right? Because that task is kind of simple. In this research, in this talk, what I'm going to talk about is we are actually looking for tasks that is actually beyond like getting from state A to state B. And we are looking at tasks that are expressed, for example, a task that's expressed by human language like this, right? This is a nerding robot. We already discretize the space. We already discretize the state space. And basically each box is a state of the Markov chain. And some of the boxes are some of the box or some of the states are labeled with, have different labels like adult, charger, baby, and danger zone. And for example, for this robot, I would like to plan for a task that is beyond going from point A to point B, but expressed in some human language like this, right? Have an example of a nursing robot, example task of a nursing robot can be always avoid the danger zone, do not return to the baby before visiting the adult or the charger, so on and so forth. Like I want my robot to find a path that, excuse me, that simultaneously satisfies all these specifications that we have here. And the reason we can define in this complex task is because we have this extra semantic layer, and based on the semantic layer, we can define complex tasks like this. So now the problem is, how do we solve planning problems with tasks that are expressed like that? Okay. Oh. So there is actually, for this task, although it looks pretty complicated, but actually there's a brute force way to solve it, right? Basically, you can employ some human engineers. You basically divide these 6 tasks and divide the whole task into 6 tasks and developing controllers or algorithms for each of them, right? But the division here, but to do that actually, if you want to do that with a human engineer, usually that engineer needs to have a lot of expertise, and also he has to make sure that when he was dividing this task, he was doing it correctly, right? That is the reason why we don't want to do it with manually, and we would like to handle it algorithmically. So the goal is, for all the tasks that looks like this, that are expressed in these similar patterns, can we develop an automated algorithm that can solve them both? Basically, I develop an algorithm. You tell me the task you want in this form, and that can automatically generate a policy. So that is the problem we would like to solve. And the way we solve this problem is actually take the old-fashioned way, that is try to develop a symbolic logic to express this task such that we can deal with it using computers. Now with the ChatGPT, there might be smarter, modern ways to do that. But for this research, we are still doing this old-fashioned approach. If you look at this approach, specifically, if you want to symbolize this kind of expression, there is several things you would like to notice. The first thing is, there are many propositional logic conjunctions, right? There's negation, there is conjunction, and there is disjunction. And all these symbols are already well expressed in the framework of propositional logic, the one that you have already learned in high school. And there are extra things that is actually expressing the order of those events. For example, something always should be always true, something should happen before another, something else should happen after the other. If you want to symbolize this expression, you need to actually introduce new temporal operators. You need to introduce new symbols to express that. And these new symbols, actually, we don't need too much extra symbols. We just need 2 of them. One is until, the other one is next. And with these 2 symbols, we can express everything like before, always, after, all of them can be expressed. And that basically boils down to a symbolic language. And basically all the other things like leap baby, go for baby, both of them, the rest of them basically can be handled by, Boolean variables. And after that, basically we can, we ended up with a symbolic language that can mathematically rigorously to capture tasks like that. And this is what we call the linear temporal logic. It is basically an extension of symbolic logic with extra temporal connectives to represent the order of how the Boolean variables should become true. And now let me give you a quick explanation on what is. So here in this linear temporal logic, we come up with a set of rules that is defining the syntax of this logic expression. I'm not sure if you are familiar with this kind of expressions. This is basically a set of symbolic rules, and you can apply these rules recursively to any formulas that is longer and longer. And when you write down any arbitrary linear temporal logic expression, you can actually, you can basically, each of these LTLs, the truth value of each of these LTL formula can be evaluated on a sequence of events, right? When you are moving on Markov chain, Markov decision process, you'll go through a sequence of states, and that sequence of states will generate a sequence of labels, and you can actually validate whether the formula is true or not on that sequence following the semantics. For example, the circle phi means that phi should hold at the next time instance. This basically means that if I observe a sequence where phi appears at the second step on the label, then it is satisfied. If phi does not appear here, then the formula is violated. Okay, and the same for the until. Until basically means that psi should hold true all the time until phi becomes true. Okay. And by doing so, basically, we can symbolize, the expression that is expressed in human language and write it as an LTL specification that looks like this, where the ABCD corresponds to the labels on the MDP. And now we can formally define our planning problem like this, right? We want to find a planning policy on the Markov decision process such that the probability of a random path generated from that MDP under the policy maximizes the probability that phi becomes true. So that is our planning problem.
How do we define the length of the path?
The length is infinite. Like you have the policy is defined as the action that you would like. The policy is basically the policy is a function from a sequence of states to the next action you would like to take. Basically, the history of all previous states and map it to the next states. And after you have this set of policy, you let the MDP run forever, and you evaluate the truth value of your LTL specification over that infinite path. So implicitly, the path is infinite, but if your truth value is only, for example, associated with the first 100 steps, then basically you can ignore the rest of the rest of the path. But potentially, this problem formulation covers the case where you are arguing about infinite paths. For example, whether the path is going back and forth between 2 points forever, things like that.
Which is the overall path? Is there a sum here or not?
There's no sum here. Like it's the cumulative. It's basically right. We have an MDP. Any path, a random path. Basically, a random path, any path under mu, right? So if you have the MDP, you have the policy, it becomes a purely probabilistic system, right? Then you can draw samples. Basically, you have a clear defined distribution for your path is, and you want to satisfy the portion about that distribution to meet the specification phi.
There's no minimum threshold for that problem.
There's no, like, I just want to know, I want to solve the maximization problem. If there's a threshold, if I solve this problem, I can solve the threshold problem, right? If the maximum value is above that threshold, it is yes. If it is below, it is wrong, right?
Can I understand, like, if your policy is given, then with that policy, you can generate a path which with different probabilities. What's the probability to generate the path by that?
Sorry, can you repeat it again?
Can we understand that objective as if the policy is given, right? Under that policy, if you run MDP, it will give you a path.
Yeah.
And what's the
what is that for satisfying that path?
Whether
yes, exactly. So yeah, it's a simple and a neat problem, right? So so now the problem is, how do we solve this problem, right? It does not look anything planning problem that we've seen in the reward-based planning problem. The reason the fundamental, in general, right? If I just write down, if it's not temporal logic, I just write down any logic expressions. I say I want to solve this problem. It is actually, there's no way that I can claim that I can solve that problem, right? And the reason why we can solve this problem is because we're not using the arbitrary logic. We are using the linear temporal logic. The beauty of the linear temporal logic. So if you look at this problem, right? if you look at this problem, potentially the policy here is memory dependent, right? The satisfaction of your formula, instead of depending on a single path or a single event, it depends on the whole path. Therefore, if you want to solve this problem by brute force, basically in the exhaustive manner, basically you need to memorize all the previous steps you have taken to determine what the next step should be, right? The policy should be memory dependent. And since we allow infinite paths, as your path grows longer and longer, basically the memory will explode and this brute force search method will not work. And the reason why it works is because we are using a special type of logic here, which is the linear temp. There are a lot of other logics where it indeed requires infinite memory, and that problem actually becomes computationally unsolvable. But here, since we are using LTL, the beauty of LTL is that you can progress the truth value of the LTL using a finite state model, which we call automata. Okay, so automata is basically, you can think of the automata as a version, as a non-probabilistic version. It's basically a Markov decision process minus the probabilistic transitions and plus several plus an accepting condition. And that accepting condition is defined in a way that, there are a bunch of, basically you will circle a bunch of special states on that automata, okay? And how does these automata help you to check the truth value of LTL? That is, you can basically, once you get a sequence of events or sequence of symbols. So for any LTL specification, you can actually generate a finite model. There's a corresponding automata. If I want to check whether an infinite sequence of labels satisfies the LTL formula or not, I can feed that sequence of label. And as you can see, the transitions of these automata are labeled exactly by the sequence of labels of that sequence. Therefore, after reading those sequence of labels, the automata will run, right, driven by the input, the sequence of input you are having here. And then you can check whether that path visits the double circled states infinitely often. If it visits that infinitely often, if it visits some of the double circle states infinitely often, then you will get, then the LTL formula will be true on that set sequence of input. Otherwise, it will be false. So does that make sense?
So going back to the last slide where there were transition probabilities.
Yep.
I'm trying to understand a little bit, and maybe what you just explained helps me understand it. But so my understanding is if you're computing a probability that the path satisfies phi, and the phi is this composition of requirements here, you said that the path is an infinite horizon path, right?
Yes.
So it would seem to me that if I picked any finite horizon of time and there were any finite probability that I violated my conditions, then if I extended my horizon out to infinity, that the probability of satisfying my conditions would grow vanishingly.
Yes.
Because is that the case?
I think yes. So I think this is actually a very good question. For LTL, that sequence for LTL, for LTL actually you don't really need to. I think your question is why do we need to memorize so many states, right? Let's say I have a task, right? I want to say I have two states A and B. I visit A once, B twice, B once, and A once B two times, and A once B three times, so on and so forth, right? Then I have to keep a counter on how many B states I visit, right? And that problem, you have to memorize it all the time. And when in the planning problem, basically all the previous history matters, and you want to follow the same patterns, so on and so forth. Actually, that problem will not be solvable here, right? Because you will have to keep your memory keeps growing and growing and growing, and finally it becomes computationally intractable. Okay. But this will not happen for LTL, so let's rule out that case. Any other questions? Okay, so basically we have the beauty of LTL is we have an automata. That automata is recording the progress of the LTL specification. Therefore, using this automata, actually, instead of memorizing, when I'm solving the decision-making problem, instead of memorizing all the history, all the previous all the previous inputs, I only need to remember where I am. If I have the LTL specification, I need to only memorize, which state I am in this finite state transition system. And that basically compress my infinite memory into a finite memory. And the rest of the problem will become pretty straightforward, right? I have the MDP, and I have the recorder I have a monitor or recorder that is recording the progress of my LTL specification. I can basically make the product, literally the condition product of these two models. I'll get a Markov decision process, a product Markov decision process whose state is a tuple of the autonomous state and the MDP state. And the rest of it will basically behave pretty much like an automata. And what I need to do here is and as you remember, the criteria on whether the LTL specification satisfies the automata is whether it visits the double circle states infinitely often, right? And this double state, we can keep those double circle states in this product MDP. And what we need to do is we want to synthesize and find the optimal policy on this product MDP to check whether to maximize the probability of visiting those circle states infinitely often. So that's how you simplify this problem.
Now you have a state.
Yes, this is actually what I want to talk about next. So it turned out that if it is a recurrency, then I'll basically skip this. If it's a recurrent policy, then you only need memoryless policy. So the reason why, intuitively, this is actually not that easy to think about, right? Because if I want to start from one path, starting from my initial state, and I want to visit certain state infinitely often, it seems to me that actually I need two policies, right? I will need one policy to lead me from my initial state to that goal state, and I need another policy to get me back there, right? But actually, what I want to say here is because here we are studying finite state Markov chains, you can actually achieve both with the same policy, and that policy is only state dependent. And the reason is because, if we look at a policy on a finite state Markov chain, it starts from the initial state, it goes through several transient states, and then it basically gets trapped in some connected components and basically looping there, right? And then what you need to find is, first you need to find a policy such that you create the largest connected component that contains the B state, that has the empty intersection with the B states. And on the rest of the state, you just try to steering your transitions to that connected component, that's it. So that's why you can do it with just one memory policy, okay? So now if the Markov MDP model, the transition probability is known exactly, then this basically reduces a LTL planning problem.
It's possible there are multiple policies will give you that probability equals 1.
Sorry?
It's possible we will have multiple policies which
Sure.
will achieve this
Yes.
probability equal to 1.
Yes.
In that case, you just randomly pick one.
Yes. Because the problem there is we are trying to find the maximum probability here, right? So the argmax there's only one max, but there may be many argmax. Yeah.
Explain why you're trying to find the largest connected component.
So the reason why, right? You don't remember the condition. Our planning goal is to try to, on the product MDP, visit certain states infinitely often, right? Visit certain states infinitely often, right? The condition of visiting this state infinitely often is that this state is a recurrent state. So it is contained in some connected component, so you can keep on getting back, right? So that's why when you are looking for the policy, you basically try to find you try to use your policy to expand to to achieve that, the largest connected component. Does that make sense?
Well, how do you define largest number of states?
The maximum is actually unique, right? It is called bottom connected component. Basically, you can prove that there are many connected components, right? But if you're starting from each state, there is a unique and largest set of states that is the connected component.
Is there really, I mean, in this class of problems, it would seem to me that there must be some favorability beyond requiring that visits be infinitely often. It doesn't address, I mean, is that to say that two different outcomes that both visit be infinitely often with the same probability are equally favorable if the frequency of visitation is very different? So, for example,
this is a good question. So in the LTL formula, right, if you call it infinitely often, it is basically a binary problem, right? There's no frequency in it. Like if I visit one state once in a million, that is still
that's
recurring.
what I'm saying. Yeah. So is it really the case that that's just as favorable as visiting it every 5 times? I mean,
no, there's no favorability. This is again, I just want to reiterate what I'm talking about. So LTL is actually not a timed logic. It's not a time task. So visit 5 times, once every 5 times, once every million times. They are viewed the same from the time perspective, from the logic perspective.
So I think a related question. So it seems the goal here is to, I don't know if it's a good analogy or not, finding a stabilizing force.
Yep.
Right, but other than stability, you will have other objectives, right? As like maybe a bit more often give you like
Yes.
reward.
Yes, that is actually, yeah, you're right. So theoretically, LTL is good because it admits that good autonomous structure. That is, from the logic perspective, that is actually a non-trivial innovation. But on the other hand, there are some shortcomings of this logic. Basically, you cannot express like visiting. You cannot easily express like visiting it once every 5 times. That's the problem that's the limitation of the logic itself.
If you change your objective instead of probability, say if I visit that, I get a reward of 1. That help you to like find policy which actually visit to those states more often?
I think so. But the problem we are solving here is, try to find out, solve the classical minimal problem, MDP, LTL, and see how we can solve a planning problem based upon that. If we have extra constraints, we can basically tweak the LTL semantics a little bit, and you can build upon this work. Okay. So basically, I think it should be clear now that, if I have, again, using this automata, I can translate LTL into a recurrency, and the recurrency statement can be defined. If I know the topology, if I know the MDP model exactly, then this basically reduces to a reachability problem. So now the problem is this. Now the problem is, what if the Markov MDP is unknown? So how do we, then we try to use reinforcement learning, right? Basically, if the MDP model is not unknown, we try to learn how to achieve the recurrency objectives through trial and error, right? And to do that, if I want to apply reinforcement learning, I want to basically convert that recurrency into a reward function, a state-dependent reward, such that I can use that state-dependent reward to guide me to find that optimal policy. Okay, so, and the reason why we can do that is because, again, the recurrency only requires memoryless policy. So that is the reason why we can hope that we can define a surrogate reward for that. And we want the reward to be as close as possible to the classical reward of the reinforcement learning. Therefore, we can just directly apply off-the-shelf learning algorithm to it instead of like devising a new and more complicated reinforcement learning algorithm. And this actually turned out to be a very hard problem. This research started like finding the surrogate reward for recurrency or more generally for LTL starts about 10 years ago. But then it is proven like 5 years later that this is actually not this is the reward is actually there's actually a counterexample for that. And also basically, you know, by surrogate reward here, I mean that it is the exact surrogate reward, meaning that the policy maximizes the surrogate reward is exactly the same policy maximizes the satisfaction probability of the LTL objective. And actually there's a counterexample for the work 10 years ago, and there's another trial probably 4 or 5 years ago, and later on it was also proved to be wrong. So it is a simple problem, but actually, and this is actually the reason that motivates us to look into this problem. So this is what we find. It is so far nobody has raised any concerns with that. Okay, so the reward basically looks like this. I'm not 100% sure. Actually, we have a proof for this, but who knows? So the reward basically looks like that. The state-dependent reward is pretty straightforward, right? You have a constant reward. You know, those B states are the states you want to visit infinitely often, right? Therefore, you assign a positive reward for that. And some of the rewards are the other rewards. Basically, you don't care, so you set it to be 0. The tricky part here is you need to have 2 discount factors instead of 1 discount factor in the usual RL setup. You need to have like 1 discount factor, which we call gamma B, the state you want to visit infinitely often, and a different gamma factor on the other states. Okay. When you are calculating the total return along the path, you add them, you add your stepwise reward. Basically, for any given path sigma, the total reward or the return is basically adding all the reward you collected along the path. But you need to, when you are calculating, as in reinforcement learning, the further the step are, the smaller the more discount you have on that reward, and the reward and the discount factor here are actually state dependent. It is not like a constant value for all. Okay. And that is actually not even, and that is not still enough. And you have to, if you want to really recover the true optimal policy, this is already a, although it has different discount factors, you can already use off-the-shelf reinforcement learning algorithm to learn it. But if you truly, so this reward is learnable, but if you really truly want to recover the optimal policy for the recurrency objective, you need to set gamma B to be a function of gamma. And you need to have all of them converge to 1. And basically, as you are learning, you need to simultaneously increase gamma and gamma B to 1 until the policy converges. And that policy will be your optimal policy. And if you are working with a finite state Markov chain, finite state Markov decision process, since in the end, there's only a finite number of policies that you can choose from. That is S cross A, right? Therefore, you actually don't need to really set gamma to be 1. There is some threshold. Once your gamma is beyond that threshold, the policy will not change. The optimal policy you'll find will not change anymore, and that is the policy you want to find. But we don't know what do we mean by sufficiently large? This must be correlated with the structure of the MDP, but we don't know what that is. But how to find that margin is actually still an open question. Here's a quick explanation on why it works. Okay, so if you look at, suppose gamma is very close to 1, and if you are starting from this connected component that is containing B, the satisfaction probability, which is all the paths you generate from these connected component will visit B infinitely often. Therefore, the satisfaction probability here is 1. And if you are applying learning, you will see that actually the reward you collected on this path will be a geometric series of gamma B. So that happens to be 1, right? And if you are starting from a transient state, right, and you basically, the total return you will collect will be the reward you got from the transient B state plus the reachability plus the probability of finally reaching a connected component that contains B, right? And that is, and you know, the transient B here, if you really want that value to be equal to the reachability probability to any component, you want to basically downplay the importance of these transient Bs. That is why you need to actually have gamma B converge to 1. Okay. And on a similar argument, you can show that actually gamma should be greater than gamma B. Therefore, and when gamma B goes to 1, then gamma should also go to 1. So that's the intuition. Basically, what the reward is doing is, it is basically splitting the satisfaction probability into a geometric series such that the learning algorithms can, the learning algorithms can only get the whole probability by visiting that state infinitely often. And the parameter gamma here, it is less than 1, and it will ensure the convergence of the RL program, the RL algorithm. So that is basically our findings. There is a proof upon that, but I think for the sake of time, I will not go through the full proof. So now the follow-up question is, you know, we have 2 discount factors. One is gamma B, one is gamma. Gamma is immediately related to, you know, the satisfaction probability. So we should keep it. But now the question is whether we can set this gamma to be equal to 1. If you see the latest work in this area, they actually all use this reward structure and brute forcefully setting gamma to 1. Okay. No, actually, one of these work is actually using this reward and setting gamma to be 1 and apply it with a deep neural networks and show that it actually can learn something. But from a theoretical perspective, you should not set gamma to be 1. The reason is actually pretty simple. This is because when gamma is equal to 1, you can write down the Bellman equation of this learning process. And this Bellman equation has multiple solutions, right? And therefore, if you apply reinforcement learning, you actually do not know which solution you are converging to. Does that make sense? Right? Generally, if a problem can be solved by dynamic programming, you can basically solve it by reinforcement learning, right? By, you know, approximating some of these unknown values by, you know, sample estimations. But that is based on the fact that your Bellman equation has a unique solution, and you know it has specifically the Bellman operator has this contractive property, and if it is not, then you don't know if the solution is not unique, then our algorithm can converge to anything. And here in this work, our latest work, we're basically showing that if you really want to set gamma to be 1, you have to smartly set the initial values of you have to actually start your algorithm from a good initial value. And in general, and that only guarantees that you can find the correct solution through dynamic programming, but whether you can generalize that in an RL setup is still an open question.
I have a question. When the solution is not unique, is it possible that all solutions are good enough?
No, these are different. The solution is not unique. Previously, I was saying that the maximum value, the satisfaction probability is unique, but there are multiple optimal policies, right? Here, the solution of the Bellman equation is the maximal satisfaction probability, right? That value should be unique. If you have multiple values for that, then you're in trouble, right?
I don't know. I'm not clear.
So basically, in some sense, reinforcement learning is solving Bellman equations by sampling, right? You know, like that's the general idea.
So the question may be related to, like, if you look at an average MDP problem, then instead of the value function, you should use the relative value function, because otherwise the solution is not unique. But if you subtract the same baseline, then you get a unique solution. Somewhat related, because you set the discount factor to be 1. to some extent, part of the problem become average reward problem instead of just computed reward.
Sorry, can you repeat the question again?
Yeah, so if you have the average reward problem, right, they have an MVP, then the Bellman equation may have multiple solutions.
Yes.
But these multiple solutions, I think the value of function differ just by offset by constant. So if you subtract the constant, let's say B0 equal to something.
This is actually not right. The problem is this. The problem is, okay. So the problem is the problem here is the problem here is the Bellman equation you have. I think in your case, it has multiple solutions, but still your I'm not sure what the scenario you are talking about. But here the problem is,
Yeah, I think the scenario may be different because what I'm talking about is the Bellman equation.
it is not a constant offset for sure. It is not a.
Bellman equation has multiple solutions, but the policy is the same. So.
Okay, no, this is different. It is different. It is different. So it is not like that. So yeah. So generally, this is because the operator itself is not contractive. If you really want to set gamma to be 1, general take-home message will be, you have to initialize your value smartly. And here are some simulations. I think we are running out of time, so I'm not sure that. And also, we can also generalize these to the game setup. Let's say, if we have, instead of a labeled MDP that only has 1 input, suppose I have 2 players in this Markov decision problem, and they take actions by terms. Then how do we solve that problem? We can basically follow the same procedure, but here there's some technicality issues with the choice of automata. And here you should use a different type of automata called deterministic parity automata. And you can actually do the same product approach and convert it into a game where you try to control what the recurrent states are. And finally, you can convert that recurrency into a reward that looks like this, which is much more complicated. Here are some simulations when we're trying to, these are some simulations trying to simulate that in a gazebo simulation where here are two different tasks, and we have one player which is the planner, and the other is the adversary who is trying to prevent this task from prevent this task from happening. Then this is the set of simulations you will see. On average, you see because of the gamma factors converging to 1, actually the convergence actually becomes pretty slow, and you see on average you need on average 1 million samples to actually see it converge to a good enough value. So that's actually all the technical discussions I want to make. And also we have also working on other projects that is related to logic. One is the statistical model checking. That is, how do you combine logic reasoning with statistics to actually verify the performance of a system that is written in this formal logic? And we develop algorithms and also applied it to evaluate the performance of computer systems. And this is our latest work is just published in Micro. And the other problem is basically combining logic with data mining. Specifically, instead of using strict formal logics on a well-defined system, we try to extend the logic reasoning from system to data. And how do we use, combine those logic with, learning methods or data mining methods to infuse logic constraints into the learning process. And the domain of application is these, flood mapping problem where you have where you have data on, you try to map flooding points on a map where your data, where you have uncertainty in your data, but you have a set of logical rules to help you make the inference. Yep, so I think that's the end of my presentation. Sorry, I ran a little bit over time, and if there are any questions, please feel free to ask.
Question? Question. Oh, sure.
Yeah, I think we already have a lot of questions during the presentation, so yeah, thank you for your attention.
Thanks, everyone. Let's thank the speaker again.
Thank you.